Well, good evening. How's everybody?
Good.
Doing well, Professor. How are you doing?
I'm doing well, thank you. All right, so we're going to start our second lecture for tonight. Got a lot to talk about. Before we do, I wanted to bring to your attention that your first homework assignment has been posted to Blackboard. Please look on Blackboard, download the PDF assignment, and that is due 1 week from today by end of day. Okay, so talk a little bit about the homework. I don't think we've talked about this yet, but please make sure you do your homework on either green engineering paper that you can scan and upload to the Blackboard, or I know a few students have used like a graph paper or some kind of a grid on their laptop and did their homework digitally. That too is okay because that comes out easy to read. But what I would want to prevent is please do not do your homework on just white lined college ruled paper or I've seen like a real harsh grid pattern. Basically, if you scan it as a PDF and I can't read it, then I can't grade it. Yeah, I guess if it's all white paper and you're using a dark pencil, that would be okay. But really, it's the green graph paper works best because when you scan it, the green disappears, the grid disappears basically, and it's really easy to read. So I would prefer use the green engineering paper. And I know you can get that on Amazon or all kinds of places that's fairly inexpensively. And of course, these days, Amazon will deliver to your home probably by the end of this lecture. You'll have it waiting on your front door. Also, when you're doing your homework problems, please just do one problem per page, or it may take several pages to do one problem, but don't try to cram all your work into one page. If the writing's too small, I can't read it. If I can't read it, I can't grade it. If your writing is exceedingly messy or sloppy or illegible, that too I can't grade. So not to make a big old deal about your homework, but just please make it legible so that I can read the work that you're doing. Also, if you would please box your final answers on the homework so I know where to look for your final answer. Okay.
Professor?
Yes.
How long would you say that we should like set aside for this first homework assignment? Like how many hours?
Gosh, I don't know. I don't know. Typically, I mean, the idea is that you're supposed to spend like 2 or 3 hours outside of class for every hour that's in class, but I don't think it's going to take you that long. And also remember to please keep up on the reading as well. We are past chapter 1 now. Tonight we're going to be going into chapter 2. But in terms of how long should it take to do the homework, I think the first homework assignment is maybe a little lighter than the ones to follow. But beyond that, I couldn't tell you. I'm not sure.
Thank you.
Sure. If we type it on Word, do you want us to use a grid or not? You're going to have a really hard time trying to type it out on Word because there's a lot of equations. But we're going to do some examples tonight. You'll get a better feel for what I'm looking for after we go through some examples. But I know Microsoft Word and PowerPoint both have equation writer. It's very cumbersome. I don't think you're going to want to do that. But if it's clear and clean and legible, then it doesn't need a grid, if that answers your question. Okay, any other questions about the homework before we get started? Okay,
Prof,
yes,
can I make the homework on the iPad?
I'm sorry, make the homework on what?
On the iPad?
On the iPad.
Yeah.
Yeah, as long as you can upload it as a PDF and it's legible, sure.
All right. Thank you.
Yeah, yeah. And like I said, I know in the past I've had several students that had one of those laptops that has where you can write on the screen, and they had a stylus, and they would actually do their homework on a grid pattern on the screen of the laptop, hand write in with a stylus their equations and their numbers and their results, and then save it as a PDF. And that came out really neat and clean. So that would be okay too. I'm sorry, Blair, did you have a question?
Oh yeah, quick question, Professor. I didn't get added on the course portal yet, so I wanted to ask if you could email me the questions for the homework too.
Send me an email and I'll try to get that. It'll be tomorrow, but send me an email and I'll respond to it.
Perfect, thank you.
Sure. And if anybody missed the first lecture, please look at the syllabus. Okay, well, I guess if you can't get on the Blackboard, you can't look at the syllabus. My email address, if you want to, well, let's do this. This is for, I know a few of you have added just in the last day or so. So let me put this on the screen. And if you can see the screen, then I'll keep this up here for a few moments. This is the email to please email me at. I don't check the other email, but maybe once or twice a week. This email goes straight through to my phone. So please, if you want to contact me, use the epratt@clarkpacific.com email address. For Eric, no, you don't have to completely write down the entire question, but I would expect that you would draw some kind of a design sketch in most cases to kind of illustrate what it is you're trying to do. Okay. For those of you who want to get my email address, was this a long enough chance to write that down? Okay, I'm assuming. Going, and gone. All right. Tonight, we're going to get into the meat and potatoes. We're going to start learning about real concrete. So again, I believe this is going into chapter 2. This is a flexural analysis of beams, concrete, reinforced concrete beams. And if I think of a simple span, concrete beam and flexure, where I'm supported at the ends by reactions, I have a uniform load across the span of the beam. Then as you load the beam, you would expect that it's going to start cracking at some point, and it's going to develop a crack pattern similar to what I'm showing. With increased loading, we might see a cracking pattern. It depends on the magnitude of the load. Clearly, if you had a reinforced concrete beam and you put a couple pounds on it, it's not going to crack. So there is a load or a threshold at which adding load does not cause cracking. And then you're going to get to a point where all of a sudden it has cracked, and the more load you add, the more cracks you will see. We can expect to see 3 stages of flexural behavior with concrete beams. So this is, I'm going to keep this here for a moment. This is just to illustrate the behavior of the concrete. So the blue curve is the stress strain behavior of the concrete. The red is the stress strain behavior of the steel. This is grade 60 steel, so you can see it's yielding at 60 KSI. And this is like 6,000 PSI concrete. So its ultimate strength achieved was about 6 KSI. So the first stage is the uncracked stage. The second stage is what's known as cracked elastic. And the third stage is what we are going to call the ultimate strength level. So keep this in mind, this curve where the steel is bilinear, but the concrete is like a polynomial type curve, where the beginning of the curve is somewhat of a straight line. So it's kind of elastic at the beginning, but then it turns into this plastic curve. Okay, so again, I've got this replicated down here. So the uncracked stage. So what I'm trying to illustrate here is this is a cross section of the beam, and this is a side view of that section. So the blue line, the vertical blue line, is just representing like the cut plane, the section that we cut through. And the first top illustration, I'm illustrating strain. So under a given loading, I have compressive strain at the top of the beam. I have tensile strain at the bottom of the beam. The second illustration is stress. So again, I'm cutting through a section of the beam. I'm looking at it from the side. And what I'm showing is that at the top of the beam, I have this compressive stress. At the neutral axis, somewhere in the middle of the beam, I have no stress, no strain. And at the bottom of the beam, I have some tensile stress in the concrete, and I have tensile stress in the reinforcement. Okay, does that read for everybody? Does everybody see what we're trying to do?
Yes.
Okay, great. So in the uncracked condition, the concrete is sustaining compressive stress at the top of the beam. That's this portion of the graph. The concrete is also sustaining tension. Everybody says the concrete can't take any tension, but it actually does take a little bit of tension before it cracks. So what's at the bottom of this is, well, first of all, you have tensile strain at the bottom of the beam or from the neutral axis down. And you have tensile stress in the concrete. You have tensile stress in the steel. Notice that this red line here represents the strain at the level of the steel. So the strain is proportional to its distance of the steel from the neutral axis. In fact, the strain is proportional at any given height based on the distance from the neutral axis. So the strain in the steel and the strain in the concrete are considered to be the same. They're bonded together. One cannot slip relative to the other. So the strain in the concrete and the strain in the steel at this elevation are the same. And then the strain in the concrete at the very bottom of the beam, again, is proportional to its distance from the neutral axis. The strain in the steel and the concrete are the same, but the stress in the steel and the concrete are not the same. The stress in the steel is much larger than the stress in the concrete. And the reason why, you can see over here. If I look at one particular strain, in fact, I think if I can do this right. Okay, so if I draw a vertical line, then at this given strain, the stress in the concrete is about here, but the stress in the steel is way up here. That's because the steel is so much more rigid. The modulus of elasticity of the steel is so much higher than the modulus of elasticity for the concrete. So at the same given strain, the stress in the concrete is much, much lower than the stress in the steel, which is represented here. The stress in the concrete is here, where the stress in the steel is way out here, much larger. Okay, so if we move on to the next stage, as I keep increasing the load, the strain is going to continue to keep going up. it's basically still going about the same neutral axis, but it's proportional. The strain is proportional to the loading. So as the load goes up, the strain goes up. As the strain goes up, notice that the strain in the concrete has gone up. But look at the stress. So what happened was the strain in the concrete exceeded the concrete's ability to sustain tensile stress. So now the stress, the tensile stress in the concrete is 0. What do we call that? What do we call it when the stress in the concrete in tensile is 0? Or a better way to say it, what has happened? Anybody?
There must be a break, correct?
Yes, yes. Only we call that break a crack. What's happened is the concrete has cracked. So here, the strain was less than what the concrete could sustain in tension. Here, the strain is higher than what the concrete can sustain in tension. So the concrete is cracked. That's why this is the uncracked, this is cracked elastic. So because the concrete has now cracked, then the tension carried in the concrete is 0. This whole bottom half of the diagram just went away because if cracked concrete can't carry tension. So the concrete is still carrying compressive stress, but no tensile stress. Does that make sense? But the steel, of course, is very good at carrying tension. So the steel is still carrying a big portion of the tension. It's just that now all the tension is in the steel, all the compression is in the concrete. And then we get to our final stage, the ultimate strength level. And what has happened now is we've added so much load to the beam that the strain in the concrete has gotten to this epsilon u. And epsilon u is right over here at 0.003. So if the strain is now way over here, then that means that the concrete is no longer acting elastically. It is now acting as a plastic material. So that's why the stress in the concrete is no longer elastic. It's no longer proportional to the distance. Well, it's no longer proportional to the strain, and it's no longer proportional to its distance from the neutral axis. So here, everything is elastic, everything is proportional. Here, that's gone out the window. So things like Hooke's law, right? Guys, remember Hooke's law, where stress is equal to strain times Young's modulus, no longer applies. Hooke's law is also out the window. So this is what's known as a fully plastic state. And this is what we're going to use to calculate what the maximum moment we can sustain in this beam is. But we have to use some tricks to account for this plasticity in calculating the maximum moment. Okay, so we have two kind of load conditions. These guys are based on what's called a service load, or a reasonable expectation of what the load really will be on this beam. This one is not going to be compared against a service load. It's going to be compared against some kind of a factored ultimate load, just to make sure that if the beam was ever grossly overloaded, would it have the strength to remain up under that grossly overloaded condition? Okay, so these are the 3 stages of behavior that we're going to go from, and they're fundamentally different. These two are elastic, but this one has concrete in tension. This one does not have concrete in tension, and this one is fully plastic. Any questions on this concept? Okay. So I'm going to introduce this concept called a modular ratio. If you notice that the stress in the steel, as I mentioned, is much, much higher than the stress in the concrete at the same location. So the ratio of the stress in the steel to the stress in the concrete is what's known as the modular ratio. We calculate the modular ratio, which is indicated by a little n. So little n represents the modular ratio. And it is calculated as Young's modulus of elasticity for the steel divided by Young's modulus of elasticity for the concrete. So in the elastic range, and this only makes any sense at all in the elastic range, but in the elastic range, you can see the slope of the concrete is E, Young's modulus for the concrete. The slope of the steel is Young's modulus for the steel. And it's the proportion of the two that dictates how much stress is in the steel, how much stress is in the concrete. Okay, so like I said, the cracking moment, you will get to a point where you have enough load on the beam to cause the beam to crack. Okay, so the flexural moment that causes the first cracking in the beam, the moving from that stage 1 to stage 2, can be found. We can find what that point is, that trigger point between cracked and uncracked. This moment is known as the cracking moment. So the cracking moment is a definite term to refer to that exact load, that moment that first causes cracking. A beam will crack when the applied moment causes stresses that exceed the modulus of rupture, as we talked about last time. So from mechanics of materials, this is the flexural formula. Sigma is equal to minus my over I. But in concrete design, we don't use sigma anymore. We use FC, F sub C. And this may be a little confusing at first, but F prime C is what we use to designate the strength that we're looking for of the concrete. F sub C is just the induced stress in the concrete. Okay, so the difference is this is a stress due to a load, and this is our design stress that we as engineers call out for. So substituting F sub C is equal to minus my over I. If we replace F sub C with F sub R, the modulus of rupture, then we can solve for the cracking moment. So if I do that and I rearrange my variables, the cracking moment, designated as M sub CR, is equal to minus F sub R, modulus of rupture, times I, moment of inertia, over Y. And finally, if we use the gross moment of inertia, I sub G, and take Y as the distance from the center of gravity to the tensile face, Y sub T, because it's going to crack on the tensile face. So you want the distance from the center of gravity to the tensile face. Then what we have is the cracking moment is equal to minus F sub R over IG, G standing for the gross moment of inertia, over Y sub T, where the modulus of rupture is equal to minus 7.5 lambda square root F prime C in PSI. Yep. And like I said, I sub G is the gross moment of inertia, and Y sub T is the distance to the tensile face. Okay, so let's look at an example. Here's the beam. This beam is 30 inches deep, 18 inches wide, and I have some steel located at 2.5 inches up from the bottom of the beam. what I would like to know is find the stress at the bottom of the beam and at the steel for a moment of 30 kip feet. Also, I would like to find the cracking moment for the following beam section. So how much load would it take to crack that beam? And you can assume that F prime C, the design strength of the concrete, is 6,000 PSI. Okay, everybody clear about the problem?
Yeah.
Okay. So for part A, I want to know what the distance is from the neutral axis to the bottom of the beam where it's going to crack. So that's y sub b is just h over 2. So 30 over 2 gives me 15 inches. The gross moment of inertia is just bh cubed over 12. So 18 times 30 to the third over 12 is 18,000 inches to the fourth. The reason why I differentiate the gross moment of inertia is because there are other measures of the moment of inertia. And one we're going to talk about a little bit later, that's the cracked moment of inertia. And then there's another one I'm not going to really get into much in this course, but it's called the transformed moment of inertia. And the transformed moment of inertia takes into account the stiffness of the steel and its effect on stiffening the whole beam. But for now, we're going to keep it simpler, and we're just going to look at the gross moment of inertia, which ignores the stiffening effect of the steel. So the stress at the bottom of the beam, F sub C, is minus my over I. So I have minus 30 kip feet. I'm going to convert that from kip feet to kip inches by multiplying times 12. Because my y is measured in inches, my moment of inertia I is measured in inches to the fourth. So if I don't convert my kip feet to kip inches, I'll have incompatible units. Okay, very important that you always make sure you have compatible units. Run this through my calculator, I get minus 0.300 KSI, or you could say minus 300 PSI. Stress at the steel. Okay, so in order to find the stress at the steel, I need to know what my modular ratio is. In order to find my modular ratio, I need to know what Young's modulus is for the steel and the concrete. Our equation from last lecture for normal weight concrete can be assumed to be 57,000 square root F prime C, which would be 57,000 times 6,000. And again, we talked about this last time. You cannot just plug in 6 KSI. It doesn't work mathematically. And don't try to take the square root of a pound per square inch. That doesn't work mathematically either. So you have to use the 57,000 square root of 6,000 and then times PSI. And that will give you 4,415 KSI. The Young's modulus of elasticity for steel is always assumed to be 29,000 KSI. That doesn't vary for rebar. All rebar is assumed to be 29,000 KSI. So my modular ratio is E sub C over E sub S, which is 6.57 in this case. Therefore, the stress in my steel is my over I times the modular ratio N. This is very important. And explain a little bit why we're using, why are we multiplying the steel times N, but the concrete wasn't multiplied times any kind of an N. And the reason for that is when we found the section properties, Y and I were based on the concrete beam, not the steel. In fact, the steel didn't even come into the equation for Y and I. Y and I are based on concrete. So when I find the stress based on Y and I, that is the stress in the concrete. But when I want to find the stress in the steel, the Y and I are based on concrete. So you have to multiply it by a modular ratio in order to convert the stress that is in the concrete at this location into the stress that is at the steel at that location. So I plug in my 30 kip feet, I convert it to kip inches. My Y is going to be 15 minus the height of the steel, which is 2.5, times my modular ratio divided by my moment of inertia, and I get 1.643 KSI in the steel, which is what you would expect. The stress in the steel is going to be much higher than the stress in the concrete because the steel is so much stiffer than is the concrete. Okay, for part B, this is normal weight concrete. So lambda, as we talked about last time, for regular weight or normal weight concrete, lambda is 1.0. So I plug in my 7.5 times lambda times square root 6,000, and my modulus of rupture is minus 580.9 PSI. Or in other words, we expect that when the stress at the bottom of this beam reaches 581 PSI in tension, it will crack. Now, in reality, there's a big scatter at, when will it really crack? It could be anywhere from 6 to 10 or 12 square root F prime C. It kind of is all over the place, but 7.5 is a good average. And that's all we're looking for, is an average value for that. So if we assume that it's going to crack at 581 PSI in tension, then the cracking moment is minus Fi over Y. So there's a negative right there. You see it's really small, but there's a minus there. F sub R is also minus, times 18,000 over 15 gives me a positive 697.2 kip inch, or 58.1 kip feet. So at 58.1 kip feet of induced moment is exactly the point where I'll develop 581 PSI in tension at the bottom of the beam, and we expect the beam to crack. Notice that, and this is just reinforced concrete industry standard, that if the concrete is in tension, we report it as being negative. If the steel is in tension, we report that as positive. And I know that's going to take a little getting used to, but concrete in compression is positive. Steel in tension is positive. Concrete in tension is negative. Steel in compression is negative. So the steel and the concrete are exact opposites when it comes to sign convention. Okay, any questions from example 1? And if this was your homework assignment, then I would be looking for a box, and a box right there, because we looked for find the stress at the bottom of the beam at the concrete and the steel, and find the cracking moment. So these are the 3 things that the problem asks for. Also, please make sure that you get your units correct. You got to have a handle on your units. KSI is kips per square inch, KSI, kip feet. Without trying to embarrass anybody, but does everybody know what a kip is? Is there anybody who does not know what a kip represents? Okay, then I will assume that everybody understands that 1 kip is 1,000 pounds. So 1 KSI is 1,000 PSI, and 1 kip feet is 1,000 pound feet, so on and so forth. Okay, so again, any questions on example number 1?
Professor, for the ratio, it's unitless, right?
Yes, it is. The modular ratio is unitless because it is KSI divided by KSI right here.
Okay.
All right.
Professor,
Yeah,
the inertia for concrete and steel are always the same?
the Young's modulus or the moment of inertia?
No, the inertia.
Well, the moment of inertia is calculated right here. That's
Yeah.
always based on the section.
Okay, okay.
So I just want to make sure I fully answered your question. The moment of inertia of a rectangle is always BH cubed over 12, but the moment of inertia of other shapes has to be calculated using the parallel axis theorem, which I'll do in the next example.
Okay, thank you.
Okay. Hazel, these notes are on Blackboard, yes. Typically what I do is between the hour of 4 and 5, while I'm on the Zoom for the office hour, what I do is I kind of go through these notes and try to find if there's any typos or anything like that. And then I upload them to Blackboard. So if you go to Blackboard right now, you'll see there's a lecture 1 and a lecture 2 that are the PowerPoint. And then each one of these lectures, I'm recording it, both video and audio. And so I record it, and then tomorrow morning I'll upload it to YouTube so you can have the video version of this as well. Okay, example number 2. Find the stress at the bottom of the beam and at the steel for a 60 kip moment. Find the cracking moment for the following beam section. This is what we call a T-beam, and use F prime C is equal to 4,000 PSI. Okay, so this is going to be the next level of complexity, I think. Solution. So for part A, we need to find the center of gravity for this section so that we know what Y is, and we also need it to calculate the moment of inertia. So the center of gravity is what's known as the first moment, right? So the area times the distance to a data point divided by the area. So I'm going to measure everything from the bottom of the beam. So I have the first area is 6 times 48 times the distance from the bottom to the centroid is 27 inches. The second piece is 24 by 9 times its distance to the centroid is 12 inches divided by the total area. And that gives me the center of gravity is 20.57 inches from the bottom of the beam. And this technique here, of course, you can carry this out to as many pieces as you need. It's just the summation from 1 to n pieces, and you just add up all the pieces. Okay, so the moment of inertia, now here's where we're going to have to implement the parallel axis theorem, because we have 2 pieces and neither of the 2 pieces center of gravity is located at the global center of gravity for the whole thing. So we're going to have to use the parallel axis theorem. Should remember this from your mechanics class. where for rectangles, the gross moment of inertia is BH cubed over 12 plus the area times the distance squared, where D is the distance from the center of the piece to the center of the whole thing. So I can look at the first piece, 6 times 48. So the width is 48, the height is 6 to the third over 12, plus the area is 48 times 6, times a distance of 27 is the distance to the center of the piece, minus 20.57 is the distance to the center of gravity of the whole squared. The second piece is 9 times 24 to the third over 24, plus the area of 9 times 24, 12 minus 20.57 squared. And this gives me a moment of inertia of 39,003. Any questions on this part of the math? Okay, so now that I have my section properties, I have my center of gravity, I have my moment of inertia, then I can find the stress at the bottom of the beam. F sub C is minus my over I. So I plug in my minus 60 kip feet, convert it to kip inches, times the distance from the tensile face. So it's going to crack at the bottom first here. So the distance from the tensile face to the center of gravity is my 20.57, divided by my moment of inertia is 39,003. And I get minus 0.380 KSI as my tensile stress in the concrete. For the stress at the steel, again, I have to find my modular ratio. So I find my modulus elasticity for the concrete as 57,000 square root F prime C. This time I have 57,000 square root 4,000 is 3,605 KSI. Modulus of the steel is always 29,000. So my modular ratio is 29,000 over 3,605, gives me 8.04. So now my stress in the steel is my over I times N. So I have 60 kip feet, 12 inches per foot, 20.57 minus the 2.5 to get to the steel, times 8.04 is the modular ratio over 39,003. That gives me 2.682 KSI. And it's positive, that's tension in the steel. For part B, again, we're assuming regular weight concrete, so lambda is 1. So my modulus of rupture is minus 7.5 lambda square root F prime C. Plug in the 4,000 and the 1. I get minus 474.3 PSI. So I can plug in now minus modulus of ratio, modulus of rupture times moment of inertia divided by Y. And PSI is 0.474 KSI, moment of inertia over Y. And I get 898.8 kip inches or 74.9 kip feet. That's the moment required to bring the concrete to 474 minus 474 PSI. And again, if this was your homework, you would box that, and box that right there. Concrete in tension is reported to be negative, and make sure you have your units correct. If you had minus 0.38 PSI, that would be wrong. Steel in tension is positive, and again, make sure you have the right units. And that is that. Any questions on example 2?
Professor, I have a quick question.
Sure.
For the stressed steel, how do you know the 2.5 inches?
Yeah. Yes, I forgot to label it on the drawing. And that's a great question. So what we're going to do, because this may happen again, the distance here from the steel to the bottom of the beam, I usually will tell you what that distance is. But if, like in this case, I forgot to mention what that distance is, then it is always safe to assume that that's going to be 2.5 inches. Like that.
Okay.
Is that like saying like that's standard, like 2.5 inches for most cases?
For most cases, yes. We're going to talk a little bit, not this lecture, next lecture, we're going to talk about concrete coverage. These beams will have some steel ties in them, and those ties will have a certain amount of concrete coverage to protect the steel from corrosion and fire. And so that coverage can vary a little bit. The size of the steel ties can vary a little bit. So this is not exact. In some cases, this may be more like 3 inches. In some cases, it could be as little as maybe 2 inches. But again, if I don't tell you what it is, 2.5 inches is always a good solid bet. Okay, did that help with your question?
Yes, thank you.
Okay. I will try to be diligent though and tell you where it's supposed to be so you don't have to guess at things like that. But just in case. Okay, so let's talk about a cracked concrete beam. Once a concrete beam cracks, then the section has to rebalance itself between the concrete in compression and the steel in tension. Any concrete that is in tension is ignored for the purposes of analysis. And in other words, concrete can carry a little bit of tension, but for strength design, we ignore that because it's so little and it's unpredictable. So we're just going to toss that and it doesn't change the answer very much. So when the concrete beam cracks, the neutral axis will immediately shift. It's going to move because it has to rebalance itself. So a new neutral axis will be found whereby the first moment of the concrete above this new neutral axis is balanced by the first moment of the transformed area of the steel below. So here's a diagram. Here's the beam before it cracks. Here's the beam after it cracks. For all intents and purposes, all this concrete is gone. For any manner of design or analysis, this concrete disappeared. As soon as the concrete cracked, all of this concrete is gone. So this is before cracking, this is after cracking. So let me put, so before cracking, the neutral axis may be, say, here, right? Because everything above the neutral axis is in compression, everything below the neutral axis is in tension, including the concrete. But as soon as the concrete cracks, you no longer have any concrete below the neutral axis. So what happens is the neutral axis has to shift immediately up. Everything above is in compression, and the only thing below in tension is the steel, right? You know, what would happen if you didn't have any steel? As soon as it cracked, it would just collapse. But because of the steel, it doesn't collapse. It can take on tremendously more load, but the behavior shifts. So here's how we're going to analyze this. This is the model. After it has cracked, this is the model of what we have. We have an area of concrete that's in compression. And then we have what's called a transformed area of steel that is in tension. Now, why do I have to transform the steel? Why can't I just use the steel as it is? And the answer is the moment of inertia is only a meaningful measure of something with one material. It doesn't make any sense at all to try to calculate the moment of inertia with two different materials. Why? Because the moment of inertia is the stiffness based on the section, and the modulus of elasticity is the stiffness based on the material properties. The two work hand in hand. If you have two different E's or two different moduluses of elasticity, then you can't have one moment of inertia. It doesn't make any sense. So in order to get one moment of inertia that does make sense, you can't have two different moduluses of elasticity. So you're going to transform one to the other. And the one we choose to transform is the one that's like the minor. We have way, way less steel than we do concrete. So we're going to transform the steel into an equivalent area of concrete based on the modular ratio. So this is the transformed area. This is the real area. This is the transformed area. This is going to be our new neutral axis. The neutral axis is such that everything above is in compression, everything below is in tension. But where is this neutral axis? We don't exactly know yet. So we're going to solve this by defining the depth of concrete as a variable x, the depth of the steel as a variable d minus x, where d is the standard concrete symbol for the depth of steel from the top of the beam. So from the top of the beam to the center of your steel is little d. So when we do this, we have a section of concrete that is b wide, x tall, and we have a section of steel that is playing like it's made out of concrete. So its area is your modular ratio N times the area of steel, and the depth at which the steel occurs is d. So from the top of the beam to the steel is little d, which means from the neutral axis to the steel is d minus x. Okay, everybody following? Okay, so the way that we find x is not just based off of area, where the area of this equals the area of this. It's not based on area, it's based on what's called the first moment. So this area times the distance from the centroid to the neutral axis has to equal this area times the distance from the centroid to the neutral axis. So it's almost like something tries to revolve around an axis. It's like spinning, and it has to have the same amount of resistance to the spinning on the top side as the bottom side in order for it to be in equilibrium. Okay, so the first moment of the concrete is going to be the area of the concrete. That's b times x. There's b times x times the distance from the centroid to the neutral axis, which is x over 2. So the first moment of the concrete is bx squared over 2. The first moment of the steel is AS, then the little t here stands for transformed. So area of steel transformed, AST, times y, which is going to be the modular ratio times the real area of steel times d minus x is the distance to the neutral axis. We equate the two to equal each other, and then we solve for x. So x will represent the distance from the top of the beam to the neutral axis. Finding the moment of inertia of the resulting section is going to yield the cracked moment of inertia, or I cracked, which is kind of the point of this exercise. We want to know how stiff is the beam after cracking. We just did some examples where we found how stiff the beam was before cracking. Now we're going to find how stiff it is after cracking. Okay, so this example is the same beam, 18 by 30. The steel is located 2.5 inches up from the bottom. It's a 6,000 PSI concrete. I have to specify the steel now as 4 number 8s. Okay, so does everybody know where to go to find the section properties for a number 8 bar? Last time I gave you some references. You can look in your textbook. You can look in the code. You could Google it online, I suppose, if you're at your computer. Or you can look at my last lecture where I had a table. However you choose to find the section properties, make sure that you know how to find the section properties, okay? It's probably the easiest way to mess up these problems is just to use the wrong area for the wrong bar. So in this case, the steel is called out to be 4 number 8s. They're in a single row across the bottom of the beam. The induced stress, or find the cracked moment of inertia, and find the induced stress from a 75 kip feet a moment at the concrete at the top of the beam and at the steel again. The solution, part A. Okay, so in order to find the cracked moment of inertia, we have to go through that process where we find the depth of the neutral axis. So the first step is the area of steel. I have 4. The area of a number 8 bar is 0.79 inches squared. So 4 times that is 3.16 inches squared. The transformed area is the area times the modular ratio. The modular ratio I got from example number 1, which was 6,000 PSI as well. So we found from example 1 that N is 6.57 times 3.16 gives me a transformed area of 20.76 inches squared. If we equate the first moments, right? So the width of the concrete is 18, depth of the neutral axis is X, D is 27.5 as given here, and the area of the transformed steel is 20.76. So by equating the two, I have bx squared over 2 for the concrete side is equal to 18, or I'm sorry, bx squared over 2 is equal to 18x squared over 2, which is equal to the area of steel times d minus x, which is equal to the 20.76, and I substituted in d, 27.5, and I got myself a polynomial or a quadratic equation. However you like to solve a quadratic equation, I don't care. Plug it into your calculator, use the quadratic equation, Google it, iterate it, don't care. However you solve your favorite way to solve a quadratic equation, solve this equation. And you will find that the positive root, there's 2 roots, one's positive, one's negative. The positive root is 6.89 inches. So that represents the distance from the top of the beam to the neutral axis. We can find then the resulting section. I can find where the center of gravity is. And I do that by taking the concrete, which is 18, and I now know it's 6.89 inches deep, times the centroid is 30 minus 6.89 over 2, plus the area of steel times the centroid of the steel, divided by the total, gives me 23.11 inches. So that means the neutral axis from the bottom of the beam is 23.11 inches. If I take 30 minus 6.89, I get the same number, 23.11 inches, right? So I found it by using the section properties, and then I found it by just using the knowledge that X is supposed to be the distance to the neutral axis. I get the same number. That's a confirmation that I did it correctly. Moment of inertia. Well, again, I just used the parallel axis theorem. So the section of concrete, I have BH cubed over 12 plus B times H times the distance to the neutral axis squared here. And then for steel, we assume that this transformed area is 1 inch high and 20.76 inches wide. So we create this, and I actually drew it to scale. We create this rectangle that is 1 inch high by 20.76 inches wide. And we do not find the moment of inertia of the steel about its own axis because it's insignificant. It actually would be 20.76 times 1 to the third divided by 12. It's not even worth calculating. So you notice that my third term is missing this I or BH cubed over 12 term for the steel. There's no point in doing it, so we just ignore it. But we do not ignore the parallel axis effect. 20.76 times 27.5 minus 6.89 squared is not insignificant. It's a big portion of the total stiffness. So that we do not ignore. And I get a total of 10,781 inches to the fourth, which is roughly a third of the gross moment of inertia. So when this beam cracks, it loses a lot of its gross stiffness. Okay. Part B. This,
Professor,
yes.
you said we ignore it because it's so small, right?
Yes.
Okay, but it's still the right thing if you just add it as well. It's just, it doesn't matter.
It doesn't matter, but it would create extra work. It would give you a moment of inertia that's like 10,782 instead of 10,781. And it would actually make your answer different than everybody else's by just a teeny bit.
Okay.
Okay. And all the reality of what we're doing, that level of detail is unwarranted because all of this is theoretical. When you talk about concrete, nothing is that exact.
Right. Okay. Makes sense.
Okay. So F sub C, the stress in the concrete at the top of the beam is my over I. So I plug in my 75, convert to inches, times y is 6.89 over 10,781, and I get 575 or 0.575 KSI in compression. Please note that we solved for the neutral axis is 6.89. It is not 15 inches. It's not to the center of the uncracked section anymore. Once the section has cracked, it fundamentally changed the properties of the whole section. So it is 6.89, not half of 30, okay? find the tension in the steel. I take my 75 kip feet, I convert from feet to inches. I have 23.11 is the distance from the bottom of the beam to the neutral axis. I found that right here. Minus the height of the steel is 2.5 times my modular ratio divided by the moment of inertia, cracked moment of inertia, and I get 11,305 KSI in tension. So I'm actually getting a pretty healthy tension now in the steel once the concrete has cracked. Okay, any questions on example number 3? All right, then I propose that we take a 10-minute break. Let's come back at 6:15. That sounds like a round number. So I'll see you back here at 6:15. All right, we are back. And let's go to example 4. So example 4, we got the T-beam event again. Only this time we're going to assume that the T-beam is cracked under this loading. So we want to find the cracked moment of inertia, and we want to find the induced stress for 100 kip feet a moment at the concrete, at the top of the beam, and at the steel. This beam, we assume we have an F prime C of 4,000 PSI concrete, and the steel is 2 number 7s. And this time I actually got the dimension in there, 2.5 inches, as it should be. Okay, so for a solution, we need to find the neutral axis. So first step is to find the area of steel and to transform that. So looking up in the chart, whichever chart you choose to use, 2 number 7s, the area of which is 2 times 0.6 inches squared is 1.20 inches squared. Transformed area then is the modular ratio, which again we found from the previous example to be 8.04 times 1.2 square inches is 9.65 inches squared. We equate the first moments. So in this beam, if the neutral axis is actually in this flange here, then as far as the beam is concerned, anything that is below the neutral axis just doesn't exist. So we don't really need to worry about going from the wide flange to the narrow web if we solve for X to be in the flange. And that's what we're going to assume at first and show that it works in that way. So we assume that once the beam cracks, it cracks all the way up to some point up here in this flange. And so the concrete is assumed to be 48 inches wide by X deep. And the steel is transformed down here at a D distance of 27.5 inches. So the first moment of the concrete is BX squared over 2, which is 48 inches times X squared over 2. And the steel is AST times D minus X, or 9.65 inches squared times 27.5 minus X. Condense that to a quadratic, solve it with your favorite method of solving quadratics, and the positive root is 3.13 inches. Notice that the 3.13 is in fact less than 6 inches, so our assumption was correct. The neutral axis is somewhere up in here in the flange. We can verify this by summing the first moments over the total area to get the center of gravity. So I only have 2 pieces here. I have a piece of concrete 48 inches wide by 3.13 inches deep at a distance of 30 minus 3.13 over 2. And I have an area of steel transformed 9.65 inches squared times a distance of 2.5 inches from the bottom, divided by the total gives me 26.87 inches. 30, total depth is 30, minus 3.13 is 26.87 inches. And so our assumptions are correct. The cracked moment of inertia then can be found of this section property. I have the concrete about itself plus the concrete times the D squared term, and then I have the steel times the D squared term. All of that feeds into and gives me 6,222 inches to the 4th for the cracked moment of inertia. For part B, do I do the F sub C is equal to my over I? So my M is 100 kip feet times 12 inches per foot times, now the distance from the neutral axis to the top of the beam now is only 3.13 inches. getting kind of skinny up there, but that's okay. So 100 kip feet times 3.13 inches divided by 62.2 or 6,222 gives me 0.604 KSI. So that's the compressive stress at the top of the beam. For the steel, my over I times the modular ratio N gives me 100 kip feet, 12 inches per foot. I have 26.87 here, minus 2.5 times the modular ratio over a moment of inertia gives me, now we're talking 37.789 KSI in the steel. Any questions on example number 4?
Yeah, Professor, how do you make the assumption at the beginning, like how it cracks?
How did I make the assumption in the beginning that it would be on the flange?
Yeah.
Okay, well, that's what we're going to do. We're going to see T-beams quite a bit in this class, and we're always going to assume, because it's almost always true, but we're all, I got tripped up. It is almost always true that the neutral axis is in the flange. So we are always going to assume that the neutral axis is in the flange first, and then we're going to test that. And if it is indeed in the flange, like it was this time, then we just keep going with the problem. But if we find from calculation that it is actually not in the flange, then we need to reformulate our equation and start over. Okay, so that's in general how we're going to do it. We're going to assume the simple, easy case first, and if we prove ourselves wrong, then we'll go back and do it the hard way.
Okay, sounds good.
Professor, can you repeat for part B for steel? Where does the 2.5 come from?
Okay. Well, we found here, this equation here, we found that the center of gravity of the whole T section, or the whole cracked section rather, the center of gravity of the whole cracked section from the bottom of the beam is 26.87 inches. Okay, that's the center of gravity of this section measured from the bottom of the beam. The steel from the bottom of the beam is given here as 2.5 inches. So the distance from the steel to the bottom of the, or to the neutral axis is 26.87 minus that 2.5 inches right here.
Okay, that makes sense.
Okay. Any other questions on example 4? All right. Next topic is we're going to talk about doubly reinforced beams. Some concrete beams will have steel detailed at both the top and the bottom of the beam. The steel at the top of the beam will be in compression when the beam resists positive moments. It tends to crack at the bottom. So any steel at the top of the beam, we call that compression steel. When steel is in compression, it takes on some of the compressive forces that otherwise would be resisted by the concrete. In lecture 1, we talked about creep, increased strain under constant compressive stress. When the steel exists in the concrete experiencing creep, that steel will serve to arrest the creep and it minimizes the strain growth. So it's something that we do as a good detailing, because as the concrete would tend to continue to strain under creep, the steel that's in the compression part of the concrete won't let it, because steel doesn't creep. So it won't let the strain keep going uncontrolled. And that's a good reason to put it up there. So when you want to calculate the cracked moment of inertia, I cracked, we consider the area of the compression steel to be 2 times N instead of just N, the modular ratio. The reason why we use 2 times N is to account for the added stress transferred to the steel from the concrete that's trying to strain under creep. Okay, so this is not this isn't even in the code. This is just kind of good detailing practice. Okay, so, and I believe this is how the textbook does it. So any steel that is replacing compressive stress from the concrete, we're going to use 2 times N instead of N. And then, just to make it even more confusing, in addition, the compression steel actually displaces concrete in the compression zone, right? Where there's steel, there's no concrete. And so the area of the concrete must be removed when adding the area of steel. This is accomplished by subtracting 1 from the modular ratio. So therefore, the transformed area of compression steel, we're going to take it to be 2n minus 1 times the actual area of the steel. We designate compression steel with this prime. Anything that has a prime on it, A prime ST, A prime S, D prime, that refers to compression steel at the top of the beam. Okay, so we're going to redo the same example, only this time I'm going to have 2 number 7s in the top of the beam. I'm going to have 4 number 9s in the bottom of the beam. And the concrete this time is 5,000 PSI. Again, I want the crack moment of inertia, and I want the stress in the concrete and the steel from 100 kip feet of moment. Okay, so part A, we're going to have to find the modular ratio, which is 57,000 times the square root of 5,000, gives us 4,031 KSI. Moment of, or modulus of steel is 29,000 KSI. Modular ratio, 29,000 or 4,031 is 7.19. The area of 4 number 9s is 4 times 1 or 4 inches squared. The transformed area of the 4 number 9s. Now the number 9s are down here at the bottom where you have tension. The 2 number 7s are up here in the top where you have compression. So the transformed area of the 4 number 9s is 7.19 times the 4 inches, gives you 28.76 inches squared. The transformed air or the area of the compression steel is 2 times the area for a number 7 bar is 0.6, which equals 1.2 inches squared. The transformed area of the compression steel, we take that to be 2n minus 1 times the area of steel. So 2 times 7.19 minus 1 times 1.2 is 16.06 inches squared. Equate the first moments. Now I have 3 pieces that I need to deal with instead of just 2. I have the area of concrete in compression, I have some steel in compression, and I have the area of steel in tension. So I need to add up each of these 3 times the distance from the centroid of each to the neutral axis. Okay, so the concrete is bx squared over 2, and then the compression steel is the area of the transformed compression steel times a distance of x minus d prime. So there's x minus d prime, which is equal to 18 times x squared over 2 plus 16.06 times x minus 2.5. All of that has to equal the tension steel times the distance from the centroid to the neutral axis, which is d minus x. which is 28.76 times 27.5 minus x. If I clean and consolidate, I get my quadratic. Solve your quadratic however you like, and you get a positive root of 7.44 inches. Now finding the center of gravity, I have the area of concrete is 18 wide, 744 high, times the distance to the neutral axis. The compression steel times the distance to the neutral axis, plus the tension steel times the distance to the neutral axis divided by the whole thing. And you get 22.56 inches from the bottom of the beam to the neutral axis. We can check that. 30 minus 7.44 is 22.56. They are equal, so that's good. And now we can find the moment of inertia. Again, I have three pieces. So I have the concrete about its own axis. I have the concrete about the global axis. I have the compression steel about the global axis. And I have the tension steel about the global axis. Add that all together, and you get a cracked moment of inertia, 14,436 inches to the fourth. For part B, stress in the concrete, my over I. This is getting pretty familiar at this point, I would think, but 100 kip feet, convert to inches, times the neutral axis depth, divided by the crack moment of inertia, and I get 0.618 KSI compression. For my steel, I have my over I times N, 100 kip feet, 12 inches per foot, distance to the neutral axis, modular ratio, moment of inertia, I get 11,989 KSI. This is for the tension steel. Now for the compression steel, now we designate this as F prime S. Is still my over I, but now it's times 2 times the modular ratio. So 100 kip feet, 12 inch per foot, distance to the neutral axis, times 2 times the modular ratio over moment of inertia, and that gives minus 5.905 KSI. It says negative because the steel at the top of the beam is in compression, not tension. Okay, any questions about cracked moment of inertia?
So Professor, the FC and F prime S, they're both at the top, right?
Not exactly. The FC is at the top of the beam. That's the concrete fibers at the very top of the beam.
Mhm.
F prime S is towards the top of the beam, but it's 2.5 inches down, embedded from the very top. So it's not exactly the very top. See, like this was 7.44. This
Yeah.
is 7.44 minus 2.5.
Oh, so I should say at above the neutral axis.
Yes, it
Okay.
is at the compression steel, which is in the top half of the beam above the neutral axis.
And can you go back to the part A?
There.
Yeah, just to make sure it's AS prime for AS. Oh, A prime ST is equals to 2n minus 1 times AS prime.
Right.
It's not AS, right? That one.
Oh, yeah, there's a typo. You got me.
Yeah. Okay.
Yeah, that's A prime S right there.
Okay. Mhm.
Yeah, and okay, how do I? That is slide 201. Yeah, we got to fix that one. Bear with me a second. 2n minus 1, A prime S, slide 201. Okay, great. Thank you. Okay, any other questions? Correct moment of inertia. Okay, so let me go back here just a second. So I want to make sure we're all on the same page. The gross moment of inertia gives you can get your stresses from a moment by using, stress is equal to moment times y over I, the flexural formula. But this only works in the elastic region. So you have your gross moment of inertia, and you can find your stresses in the concrete before the beam has cracked because it's still in the elastic region. You can use the cracked moment of inertia and find your stresses in the beam after cracking, as long as it's still in the elastic region. Remember I said from lecture 1, the elastic region is about up to 40% of the strength of the concrete. So in this example, the strength of the concrete was 5,000 PSI. So 40% of that is going to be 2,000 PSI. And at the bottom here, we found that the stress in the concrete is only 618 PSI, well below 2,000. So that means that this procedure, this method of calculating stress in the concrete and the 2 rows of steel is valid because the concrete stress is still in the elastic range. It's still less than about 40% of the final strength. But if you get in beyond that, if the stresses are higher than about 2,000 PSI, then here's the catch. You can no longer use the moments of inertia. Moments of inertia kind of become sort of meaningless after the beam is no longer in the elastic region. Okay, so that's our next topic, the ultimate strength level. Once you get from loading that keeps you in the elastic range, whether you're cracked or not cracked, once you progress to the point where you're beyond the elastic range, now you're into this ultimate strength level. And you can't use the gross moment of inertia. You can't use the cracked moment of inertia. You can't use moment of inertia really at all in this range. It's not a meaningful measure anymore of the section properties. Okay, so what do we do? Okay, so at the ultimate strength level, we're going to make some assumptions. But the assumption 1 is that the strain follows this profile. You've got a maximum strain in the top of the concrete beam, and you have a strain at the level of the steel. It is assumed at this point, like I said before, all the concrete has cracked below the neutral axis. So there is no concrete. There's no tensile stress in the concrete because it's cracked and gone. But the concrete in compression is most definitely still there above the neutral axis. Neutral axis will be right at this point here, or right where the strain is equal to 0. And this concrete is most definitely there in compression, but it's not linear anymore. It doesn't look like a triangle anymore. It looks like a parabolic curve. And that's the reason why the moments of inertia, just the concept of moment of inertia, is no longer applicable because you're not elastic. You're not following an elastic curve anymore. Okay, so for the ultimate strength, for strength design, we have 8 assumptions that we're going to make. First assumption. Our assumption is going to be that the strain in the concrete is equal to the strain in the steel. And all that is really saying is that the steel embedded in the concrete through a chemical bond, through adhesion, and through a mechanical bond of the concrete biting into the ribs, or the steel ribs biting into the concrete, forms a mechanical anchorage. Through those mechanisms, whatever the concrete is doing, the steel is doing exactly the same thing. What it means mathematically is that if the blue line is the strain profile of the concrete, then the red line is the strain profile of the steel. The steel and the concrete have exactly the same strain at the same height in the beam, okay? You don't have the steel going off and doing one thing and the concrete doing something else in terms of strain. Strain-wise, they're the same. Stress-wise, they are completely different. The steel is taking a whole bunch of tensile strain. The concrete's taking 0 tensile stress, but the strain are the same. Okay, so that's assumption number 1. Assumption number 2 is that strains are linear. And all that is to say is that when you draw a strain diagram, this line is always a straight line. The stress is not linear, and we're not even going to pretend that it is, but the strain is. We assume that the strain forms a straight line, which means if you know where the neutral axis is, and you know what the strain in the concrete is, then you can calculate the strain anywhere else on the height of the beam. Number 3. As we mentioned before, the modulus of elasticity for steel, E sub s, is always taken to be 29,000 KSI. Number 4, plane sections remain plane. This has more to do with curvature. So as a beam bends, you form like you'll have a deflection or a curve in the beam. But if you take perpendicular to the surface of the beam at any given point, that section remains plane. I could draw a little sketch here. So if a beam has a deflection, then if I draw a line perpendicular to the surface, that line may look like that. If I draw a line here perpendicular to the surface, that looks like that. And that looks like that. And where all these lines meet together at a singular point, that distance, that radius, is what's known as the curvature of the beam. But these sections always remain plane and perpendicular to the surface. So that's a basic assumption that we make in order to calculate moment curvature, deflections, and that sort of thing. Number 5, concrete in tension is ignored. So what that means is, see, here's the neutral axis. Anything below the neutral axis, there is 0 stress in the concrete. That is not exactly true, but it's close enough, and it makes the problem a lot more simplistic to solve it much more readily with a very, very small margin of error because you ignored some concrete in tension. So for the purposes of this class, and the textbook and the code all do it the same way, we are assuming that below the neutral axis, there is no concrete. There's no tensile stress being resisted by the concrete at the ultimate strength level, okay? Again, at a surface level or at the elastic level, absolutely the concrete has to take tensile stress because it's below that cracking level. But at the ultimate strength level, the concrete cracked a long time ago, and we assume there's no concrete left to take any tension. Okay, number 6, we assume that the concrete is inelastic at strains epsilon c at about above 0.001 inch per inch, which is also about that 40% of the strength of the concrete. Number 7, we assume that the section is considered failed at epsilon c above 0.003 inch per inch. So this 0.003 you see right here, that's in the code. There's a code section that says, thou shalt assume that this is your failure strain. If you do some real concrete testing, that can vary quite a bit, but it doesn't actually change the final answer very much at all if it does vary. So the code says, yeah, we're just going to make this simple. Everybody use 0.003. And number 8, the compressive stress in the concrete can be approximated with this thing that's called the Whitney stress block. We're going to get into that next time, the Whitney stress block. But what it does is it takes this very interesting shape of concrete compression and it replaces it with this very boring shape of a block, a rectangle. So instead of calculating the center of gravity and the magnitude of stress in this parabolic shape, we're allowed to just use this boring old rectangular shape instead to simplify the calculations. And like I said, we'll get into that next time on how to do that. Any questions about the 8 assumptions? Okay. So to calculate the nominal strength of a concrete beam, what we're going to do is we're going to assume that the steel will always yield prior to the concrete crushing. And this is required by code. So let me go back here a little bit. What this is assuming is when this concrete reaches the 0.003, where we assume that the concrete has crushed, the steel is always going to have a strain more than the yielding strain, always. And the code has provisions that make sure that the steel will always have a strain in it bigger than the yielding strain. We don't ever want to have a beam where the concrete crushes before the steel yields, okay? So going back here, since we will always assume that the steel is going to yield before the concrete crushes, then the tensile force is just going to be T equal to the area of steel times the yielding stress, F sub y. Makes it super simple. We don't have to try to figure out what the strain in the steel is to try to figure out what the stress in the steel is. We always use F sub y. Now the compression force, the concrete compression force will always be the integration of compressive stress from the top of the beam to the neutral axis and across the width of the beam. One approximation for concrete stress as a function of strain is, okay, so hopefully this isn't going to confuse you. In the next lecture or two, I'm going to introduce the Whitney stress block. And the Whitney stress block is the really super simple, easy way to approximate the compressive stress in the concrete. What I'm showing you for the rest of the lecture today is a more accurate way to show the compressive stress in the concrete. It's just for your information. We're not going to use this to calculate the strength of the beam. We're going to do it the way that the code does it with the Whitney stress block. I just wanted you to be aware that what's happening in the concrete is so much more interesting than what this Whitney stress block would lead you to believe. So instead of the Whitney stress block, which we're going to use the rest of this semester, you can use this expression where the stress at any given location in the concrete is 2 times F double prime C times the ultimate, or times the strain in the concrete over this nominal strain epsilon naught. So what goes into this equation, F double prime C is 90% of F prime C. Epsilon naught is 1.71 times F prime C over the modulus. And if you plot this from 0 to the crushing strain of 0.003, this is what the curve looks like. So at the neutral axis where the strain is 0, you have 0 stress. At the top of the beam where the strain is 0.003, you have this stress. You actually have a maximum stress somewhere in between those points at epsilon naught. At epsilon naught, right here, you hit your maximum stress. So you can use this equation to sum the total compressive force in the concrete by using this expression. The total compressive force is equal to the integral from 0 to C to the neutral axis times a stress of 2 times F double prime C times the width of the beam times the integral of this part. This is the variable part, where C is the distance from the neutral axis to the top of the beam. B is the width of the compression zone. Epsilon U is the ultimate strain taken at 0.003. And epsilon C is taken, this is just a proportionality based on X, where X is a variable distance from the neutral axis to the top of the beam. And you're integrating a function of X dx. So when you do that, you also need to know where the center of gravity of that compressive force is. So the center of gravity is the same expression, only you add an X to it to get the first moment. You integrate this, and then you divide. I actually have that upside down. I got to fix that. A prime is equal to Q over C. So sorry, this is supposed to be Q over C, not C over Q. But A prime is the distance from the top of the beam to the centroid of that compression, and that is equal to Q over C. Oh, there it is. Now it's fixed. Now that you have C and T and you know their locations, you just sum your moments to get the capacity of the beam. So you can sum your moments about C, you could sum your moments about T, or you could sum your moments about the top of the beam or the bottom of the beam or just about anywhere really to get your capacity. So Mn, the nominal capacity of the beam, is equal to the tensile force times a distance of D minus A. Let's see, kind of running out of time. I did an example. Let's go through this, and I could do this in just a couple of minutes. So the area of steel is 3.16, that's 4 number 8s. The tensile force in the steel, again, remember, we're always going to assume that the stress in the steel is the yielding stress. So you have 3.16 times the yielding stress of 60 gives you 189.6 kips. The concrete properties, the modulus of 6,000 psi is 4415 ksi. Epsilon naught is 1.71 times 6,000 over Young's modulus, gives you 0.0232. That is the strain where we assume the maximum stress. F double prime C is 90% of F prime C, which is 0.9 times 6 is 5,400. So then we can evaluate the integral. I plug in my 5.4 KSI, the width of the beam. In here, I plug in the maximum strain of 003 and epsilon naught of 00232. I evaluate this, and actually little c is a variable. So what you do is you can plug this into a spreadsheet and iterate little c until the tension equals the compression. And that comes out to be 2.567 inches is the distance. So then I evaluate this from 0 to 2.576. I get 189.6 kips. Compression has to equal tension. So 189.6 equals 189.6. I then evaluate Q, which is the same expression. It just has an extra X in there. I get 195.1 kip inch. So A hat is 195.1 over 189.6. So the centroid of the compression is 1.03 inches down from the top of the beam. Therefore, the capacity of my beam is the tension force times 27.5 minus that A hat distance, which gives me 5,019 kip inches or 418.2 kip feet. Okay, so what does that mean? What did I do? What I did is, assuming that these for number 8 will yield at 60 KSI, and assuming all the section properties that we did here, then what this means, at 418.2 kip feet of applied moment, the steel will have already yielded a long time ago, but at this magic number is when the strain in the concrete will exactly hit that 003 point. And that's where you basically assume that the concrete in the top of the beam crushes and the beam collapses. That would be the failure load of that beam that crushes or collapses the beam. Okay, so when the rebar starts to yield, the beam has not failed yet. But when the concrete reaches 003, it crushes, and that is what fails the beam. Okay, we are not going to use this method for calculating the stress in the concrete, the compressive force in the concrete, the centroid of the compressive force in the concrete. We're not going to do that again. This was just an example to show that there's alternative methods to calculate these properties and to kind of show you a more accurate view of what the concrete's actually doing. But from here on out, we're going to use the Whitney stress block method instead of this method. And you'll see that it is much, much simpler. Okay, so I just want to make sure everybody understands I'm not teaching you this method to be applied. I'm just teaching it to you to show you that there's alternatives to the Whitney stress block method. I actually do use this method for various purposes. I'll use this method if I need to evaluate the concrete at some other strain other than 003, where the Whitney stress block doesn't apply to any other strain other than 003. So this method is much, much more versatile than the Whitney stress block method. But this is an intro to concrete design, so we shall not speak of it again. That is pretty much what I wanted to present tonight. Does anybody have any questions they'd like to ask of me?
Yeah, Professor, are we supposed to be able to start solving homework number 1?
Almost. you can start on it. There's a few concepts in homework number 1 that we're going to hit in the next lecture. So parts of it that you can do, parts of it that ask for the gross moment inertia, the cracked moment of inertia, M cracked, those sort of things that you have enough information to do. But there's also some things in there about spacing, rebar, and coverage and things like that that we will cover in the next lecture on Thursday. And that still gives you the whole weekend to finish it up.
Okay.
And that was a good question. Any other questions?
I was wondering if you posted the solutions to the homework after we turn them in?
Yes, I do.
Okay, thank you.
Uh-huh.
And Professor, for this example, this is beyond elastic, right?
This is way beyond elastic, yes.
Okay.
The strain of 003 represents that magic point when the concrete literally crushes and fails. So it's so far beyond elastic, it's right at that failure point.
Right. Okay. Thank you.
Sure, sure. Anybody else? Okay, also remember, we're gonna talk again on Thursday, but remember you have an office hour from 4 to 5 o'clock on Thursday. You also have an office hour from 4 to 5 o'clock on Tuesday, and the homework isn't actually due until midnight Tuesday night. So that gives you one more opportunity to ask any questions, anything that you got stuck on over the weekend. And then you have from the end of lecture at 7 o'clock until however late you want to stay up, but you have until midnight to finish it up. So you have 2 more opportunities for office hour if there's something that's tripping you up with the homework. Okay, so with that, we will close out. I will post this to YouTube tomorrow morning, and we will see you on Thursday.
Thank you, Professor.
Thank you. Have a good one.
You too.
Thank you, Professor. I'm gonna send the email for the homework right now.
Thank you.
Okay.
All right.